Alright, hello everybody and welcome to my YouTube channel. So today, I guess I'll start by spinning off this series. So self-evidently, based on the title of this YouTube video, I will be coding in C and C++ until I get an internship. Hopefully in embedded systems, but I'm also looking for other internships as well in software engineering and whatnot. So electrical engineering. The goal of this series should just be to keep me motivated to keep on coding and working for the summer, because unfortunately, although I did land kind of an internship, it's more of a much smaller company, and it's more of a contractual basis, I guess. So it would be great to have a good internship by the next year, and hopefully I want to get started by learning C and C++, also for embedded C programming. I won't be updating or editing these videos too thoroughly. I'm just gonna be like coding, I guess, in the background. And yeah, like I said, these videos are just to keep me motivated for the future. These videos will probably be around like 2 hours and 30 minutes approximately, maybe longer depending on how much time I have. Usually the videos, at least the way I want to structure them, is first hour should be spent towards learning more C fundamentals, and then another hour and a half should be learning more about embedded stuff. So I actually have an STM32 microcontroller, right here. Obviously you can't see it because there's no face cam, but I'll probably be programming on that. So a bit more about me. So I'm actually a second year student in studying electrical and computer engineering. I have some experience in C/C++, primarily just through 2 courses, but I don't think I have like that much of an in-depth understanding of it, which is why I want to start this YouTube channel and use this summer to hopefully learn a little bit more about this stuff. So yeah, I hope this is helpful for you guys or whoever's watching. I don't think anybody's gonna watch this channel, but yeah. So I guess we should get started. So I'm gonna first start off. I'm gonna start by starting up the timer. Obviously, yeah, and then I will. So then I'm going to go on to the learnc.org. So that's what I'm going to be using first to. Although I do have learned C a little bit, I think I want to review a couple of things before I move on. I'd probably skip a couple topics, like maybe I won't cover like conditions or for loops or while loops, but I will cover some like strings or static or more advanced concepts, because I haven't really. It's been a while since I learned it. I think it's been like 1 year, so I actually formally learned C. And then there's also stuff in like embedded C programming, which I should probably learn as well. So yeah, let's begin then. So I'm gonna first start off with variables and types, just to get a brief understanding first, and then yeah. Okay. Let me get my iPad real quick. Okay. All right. I'll just put my microphone a little bit closer. Okay. So variables and types. Okay, so C has several types of variables. There are a few basic types. So integers, whole numbers, which can be either positive. So yeah, we know this. Unsigned integers, whole numbers can only be positive. Yes. Okay. Unsigned floating point numbers, real numbers, floating double. And structures, yeah, you know, structs. It's on most computers today, the 32-bit number, which means okay. Yeah, okay. Okay. So, all right. So, from my understanding, yeah. So unsigned would just be from like 0 to 4 billion approximately. Signed is from using 2's complement would be from negative 2 million to 2 million. Okay, yeah. Damn. Okay. Damn it. Coding in C++, it's been a while since I've touched this stuff. Usually it's defined in the following section. Okay. So, yeah, so let me open up VS Code real quick. Okay. So, I'm going to start the first C program. So, chapter 1.c. Okay. Yeah. So, okay, so let me import the standard library. std stdio.h, and then let's start with our own program. So, no, it's like this. So hello world, beginning. So how do you compile? Compiling C program. Command line, Linux. Okay, so it's basically, okay, so it is the same thing as C++. Okay. G++, GCC, chapter 1.c.o /executable. Yep, there you go. Perfect. Runner C++ chapter. Yep. So, okay, so I guess that's our first C program. It's been a long time. Okay, so this is the standard library in C. So this contains all of the standard input and output streams that we would need in C. Okay, perfect. It's just like how in C++ we have stdlib.h, stdio.h. Okay. Okay. Perfect. Okay. Perfect. Okay, so let me go back to the main website now. So, okay, perfect. Okay, so integers, whole numbers, which can be either positive or negative. So, yeah, we read through that. So, from my understanding, an object would just be some memory, some location in memory where some value is stored. So you have integer. Can be 4 bytes stored in that particular area of memory, which will be allocated there. Yeah, okay. Next tutorial. Okay, so okay, so let's get started. I want to hopefully, so just quick primer on how arrays work. So in C++, so it's going to be int array 10, right? So this is just going to be an array that holds 10. So let me quickly. Actually, let me just go straight to display capture. Actually, I think it's probably more better that way. So, okay, so int, yeah, so integers in C, rather, sorry, arrays in C, okay. I should probably get a book on this, to be honest with you, but unfortunately, yeah, maybe that's for later. Arrays are used to store instead of declaring. Okay, so that's okay. So it's basically the same as C++. Okay. So array 10. So okay, good. So let's start off with let's do for int I equals 0. I is less than I plus plus I, and we'll just be like, okay, array I is equal to I don't know. Let's do int I equals 0. Sorry, I plus plus. Okay, and then for int I equals 0, I is less than 5 plus plus I. Printf. And that's how it is. /n. That's gonna be the escape operator, escape sequence. Sorry, and I forgot what the D is, but array I. Okay. Good. So let's start with them comment out printf. So yeah, so just covering some basic stuff just to make sure I understand it. Okay. What the fuck? Interesting. Oh, no wonder. Sorry. That's a very silly mistake by me. Shoot. I probably shouldn't use this same very well. Yeah, there you go. Should work now. Okay. There you go. Okay. So I guess basic program on how arrays work. I wish there was a little bit more in-depth stuff into this. Okay, learning C but PDF. Okay. 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 General syntax for declaring one-dimensional array is so type, array name, and then size. So yeah, where type could be built in an array is done like this. It holds an indeterminate value to ensure you can do this. Okay, arrays can have initializers. Addition the first value in the list. There's some heavy construction happening near my house, so apologize in advance if this bothers you. By the way, the first episode was going to be recorded, but I'll try to do live streams later on. Wow, this is... I've never seen this before. The first value in the list was the first member of the array. Okay, so interesting. So yeah, comment this out. So if, for example, if you were to have something, so if you were to, so we were to declare an array, and now we're gonna initialize it. So let's do 1, 2, 3, for example. Right. G++. Okay. So it does. So in C, all of the other contents of the array will equal 0. Good. Okay. And I've never seen this explicit initialization before. This is very cool. In C, into array, so you can like initialize like each index in particular to have a particular value in the array. So we know that, like, for example, so we know that an array is like contiguous. It's like some sort of data structure that holds some data slash values in a contiguous memory locations. So if we know, like, so I'm guessing by writing this line of code, usually the compiler will just interpret this, and it will just like create if it knows, oh, right, because it'll just set it to 0. That's how it knows the memory location already. So if we do, let me try this actually. So I want to see this work. So it's like the index equals whatever, right? So if we do like index 1 is equal to, index 1 is equal to like 4, index 2 is equal to, index 3 is equal to 1, and then index 2 is equal to 2, for example. Then it should be 4, 2, 3, and then the first index will be 0. So let's try that. Oh, sorry, non-trivial, this is not supported. Oh, what the heck? I'm reusing the right version of C. Okay. Shoot. Okay. So yeah, I really don't want to use AI right now. Trying to figure it out by myself. Oh, wait, hold on. C. Oh, shit, because G++ is that's so interesting. G++ versus GCC, right? Bro. Oh, damn, I look so stupid right now. I am so, yeah, I probably should have paid more attention to this type of stuff. Oh well, I guess we're getting somewhere. Yeah, so GCC is for compiling C programs, G++ is for compiling C++ programs. So no wonder the compiler can't understand how to do this, because I'm guessing this whole process of explicit initialization is only possible in C, and as if G++ is a compiler for yeah, okay, perfect. So let's see it. Let's see this working. Yeah, okay, and of course this will create a bunch of memory locations because it's not an array. So okay, so let's retry this again. I'm going to delete this because I don't need this anymore. GCC chapter 1C auto executable. Okay. So there you go. Yeah, so it does 4 and then 2 and then 1, which is exactly what we want. Correct. Perfect. Amazing. Okay. I didn't even know this was possible. So what is this called? This is called explicit initialization of an array. You can explicitly initialize I did. So this is like a C feature that C++ doesn't have. It's interesting because I don't think you can do this in C++, but I have depth. So yeah, okay, perfect. In most cases, the compiler can deduce the length of an array for you. This is achieved by leaving the square brackets empty. Int array 1, 2, 3, and so an array. This is like very old though. I don't know if this is up to date. Yeah, sorry guys. I kind of just started this. Next episode I'll probably just figure out what resources to learn more in depth. But so far it's working for me so far. So okay. So in most cases, the compiler can deduce the length of an array for you. This is achieved by leaving the square brackets empty. Okay, so yeah. So I'm guessing if you were to do explicit initialization, based on the highest index, it will deduce the size of the array based on the highest index you explicitly declare. Okay, perfect. And you can be like, that's pretty cool. Okay, good. All right, so we can move on. In most cases, the compiler can deduce the length of an array for you. So yeah, we can test this out ourselves. So obviously, I'm not going to do that right now, but I think I understand the idea. Variable length arrays. C99. When is C99? Okay, 1999. Latest version of C. Okay. 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 So variable length arrays, VLAs for short, were added in C99 and made optional in C11. They are equal to normal arrays with one important difference. The length doesn't have to be known at compile time. So compile time in this case being like when the program actually starts compiling each element in the memories. It's allocation time. VLAs have automatic storage duration, only pointers. Okay. Interesting. I was just about to ask, like, what are the applications, and it's just like VLAs are potentially dangerous. If the array in VLA in the example requires more space on stack than available, in the stack will overflow. Yeah. Okay. Cool. Yeah, and as we know, the stack is. I should probably review that a little bit more. Stack in terms of the computer organization perspective. Computer architecture perspective. Yeah, we'll do that like a little bit later, or at least soon. Iterating through an array efficiently in row major order. So arrays in C can be seen as contiguous chunks of memory. More precisely, the last. Okay, so we know this. It's the same in C++2. The last dimension of the array is a contiguous part. We call this the row major order. Understanding this and the fact that cache faults load complete cache line of the cache. Okay, so cache is just like something the processor. It's just a smaller unit of memory that the processor accesses. So so you have 10,000 by 10,000 array. Oh, yes, this makes a lot more sense, yeah. Potential load array 0, 1 in the cache. Yeah, so this is, I learned this in computer organization. This is pretty cool. Okay. Okay. Okay, interesting. Yeah, this makes sense. Let me write this down. Alright, sorry about that. Just something. So anyway, okay, yeah, so let's move on to section 1.3, 10.3, array length. So arrays have fixed lengths that are known within the scope of their declarations. Nevertheless, it is possible that it's sometimes convenient to calculate array lengths. In particular, this can be determined. Okay. Perfect. Okay. So you have an int, you have an array, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So size of the array will tell you the array size in bytes. So assuming that um, so if we know that obviously an integer is 4 bytes, and in this particular case there is 10 elements, we know that therefore 4 times 10, there'll be 40 bytes of data inside this array. So we can just let me okay, so I'll just going to, so let me just move on. So I'm just gonna put something like this. So I'm gonna comment this out real quick, and then I'm going to do this into array. Okay, perfect. So we don't specify the size because we already have the size specified here. So and then, so let's do this. So get rid of this. We don't need this. And then, okay. Yeah. So let's do size t. So what is the type size t? Size t in C. Okay. And it's an Einstein integer type used to represent the size of objects in bytes. Okay. So size t versus int. Size unsigned int versus size t. Okay, because it might be bigger equal to or smaller. Okay, interesting. So size t is just like optimizes for you. It's the size for you because it couldn't, instead of just having unsigned, because that's limited. So okay, so size of, and then let's do array. Okay, print f. I'm not sure what the specifier is here. I don't know if this is correct. 40, right? Perfect. So it gives you the total. So an array is like, there's gonna be 40 bytes, right? So now if you want, so it makes logical sense to then take 40 to find the amount of elements, right? If we know that there are 10 elements, each element has 4 bytes. And then, so to find out the amount of elements, we just delete by the amount of bytes of each element, right? So that's going to be, yeah, 10, right? So size t, and we just, oh, we do size t also for, okay. So like, what's the size of array? So that's going to be 40 divided by size of array 0. This is perfect. Okay, so let's do that. And we got this. We got this. We got this. Shipments. Ah, bro. I finished. 10. Good shit. Okay. Okay, so there you go. We, yeah, makes sense. However, in most contexts, we're in array pairs. Okay, however, in most contexts, we're in array pairs. An expression is automatically converted to case to a pointer of its first element. Ah, okay, okay. That's interesting. Where an array appears, it is automatically converted to. So I'm guessing this is what it means, right? So. It's good stuff. Perfect. So you just, that's very interesting. I did. Okay, 12 pointers. So. Okay, perfect. We got. Okay, so let me continue from here. The function can be implemented like this. Note in particular that although the declaration of parameter input resembles that of an array, it in fact declares input as a pointer. It is explicitly equivalent to declaring input as int star. Okay. Star input int star. Okay. Arrays cannot ever be actual arguments to functions because they indicate pointers. Okay, it is very common to error. Oh, damn. Okay, that's very interesting. Okay, so let me, just to verify this, let me put this into the code right here. Okay, let's see if there's a compilation. There is a compilation issue. Okay, so okay, perfect. So the gist of it is that whenever you include like an array in an expression or like for example a parameter in a function, uh, you'll automatically convert it to a pointer. You'll automatically decay it back to a pointer. So if we were to like derive like its length, it's not possible because the pointer doesn't tell you like the length of the array. It just tells you like the first element of the array. So perfect. So okay, so yeah, perfect. So int square brackets input equals int star input. So it's just going to be a pointer to input, which is input being the address of the first element in the memory of the array. Do not do this. Okay. This is the exact same. I haven't taken a class on compilers yet, but this seems pretty cool. Okay. Okay. Okay, so multi-dimensional arrays follow the same rules as single-dimensional arrays when passing them to a function. However, the combination of decay to pointer, operator precedence, and two different ways to declare a multi-dimensional array may make the declarations of such functions non-intuitive. The following example shows the correct way to pass multi-dimensional arrays. Okay. So they have the void like int x assert size. What the fuck? Yes, when passing a multi-dimensional array function, it decays to a pointer. I'm surprised why they have pointers like right after arrays. Like they're talking about pointers, but you haven't even learned what a point. I mean, it's the reference book. I guess it's a good book for me because I did learn this stuff previously. It's just going over some stuff I might have missed. Okay. Okay, I see. Interesting. Okay. Okay, so we can skip this. So multi-dimensional arrays. C programming allows multi-dimensional arrays. Here's this project form a multi-dimensional array declaration. Okay, size 1, size 2, size 3. For example, the following declaration: 5x, 10x, 4 integer array. Yeah, so you can have n-dimensional arrays, big n-dimensional arrays. The simplest form of multi-dimensional array is a two-dimensional array. A two-dimensional array is in essence a list of one-dimensional arrays. Mxn, and we can write as follows, where rows, m rows, and n columns. Right? Okay, so that makes sense. It's same in C++. So just be like int array okay. Okay, good. Okay, so int array, so you can be like m, and this is gonna be the amount of rows and columns. Good stuff. Good stuff. Okay, so it's multi-dimensional. You would have like 3 rows, 2 columns, right? Something like that. 3, 2. Oh yes, and they were alluding to this last time with the whole cache lining and stuff. So it is a row major language. So okay, so row major language implies that like so yeah, so it's gonna just be like this. So it's gonna be like 1, 1, 1, 2. The column major would be the opposite. So it's going from left to right. It's going top to bottom. Yeah. Okay. So that's a brilliant graphic, by the way. So I think I might as well just write it down. Perfect. And that works good. So thus every element in an array is identified by the element of the name form Aij, where is the name of the area. A 3D array is essentially an array of arrays. It's an array or collection of 2D arrays. An array of 1D arrays. Yeah, that makes sense. Likely that most of the arrays that are created will be of 1 or 2 dimensions. Okay. So, guessing the third, yeah, so define array and access array element. So what we learned from this section 10.5 is just that the multiple dimensional arrays can exist, and of course C is a row major language like C++. So it's implying that rows will come first when we initialize, so it'll be mxn array, so int array mxn, where m is rows and n is columns. So yeah, I think same C++. Okay. Okay, so n is an arbitrary array of 10 integers. Use size t. Okay. Initialize elements of array n. So for int I equals 0, I is less than r len. I plus plus n I equals I plus 100. I to I plus 100. So output each array's element value. So for j equals 0, j is less than r len plus plus. So print f element. Okay. Okay. Yeah, so we just did this. Okay, cool. Sometimes it's necessary to set an array to 0 after initialization has been done. So okay, but interesting. But why didn't we just okay. So, but wait a minute. So, let me think about 1 second. So let's say we have an array, right? So we have created an array 3, 10. Okay. So for int I equals 0, I is less than 10 plus plus I, and then we'll just be like array 3, print f, d. Let's just escape sequence, get the escape sequence in there, and then array 3. Okay, so array I. So what is the difference between like okay. Oh, solution. Yeah, we can just set it equal to 0 like this. No, unless I'm mistaken here. After initialization. Yeah, this is current not initialized. Yeah, this is not initialized because nothing is. But you could just initialize it like this and it perfectly does the same function. So I don't know what the difference here is. But I guess it's just for clearing. Let's see. I mean, you can do it like this, but I thought this was the way, but I'm not sure. I mean, you could just initialize it like this if you want to clear it to begin with, but I don't know what this point of this is. I think this is useful, like if you already have a full array and you want to clear it, which makes sense. But it seems like I didn't even know this was a thing though. You can do this in one shortcut, which is just memset, the memset function. What is memset in C? Okay. Okay, so that makes sense. So memset is just to fill a block of memory with a particular value. Right. So that makes sense because yeah. So what essentially So what I'm guessing what this thing does, says. So what it does, since an array has contiguous memory locations, if we were to take like some array, right, and then we were to 0, it will start off at the pointer of the array, which we know the memory, we'll start off at that memory address. And then we will, I think we will just add the address and traverse through it, going it to 0. But we could do this not only just for 0, we could do this for any number we want, any statistical phone number. Let's do like 10 times. Okay, we have to include. Good. So let's do that. Oh, GCC. Good. So what we also do mouse set. Ooh, that's very interesting. Why does it do that? That is quite strange. What is it? What happens if I do this? That's a different. That's a character though. That's a char. So, what is the third? What is the second parameter? Oh, so this converts it to an unsigned char before it fills. Okay, damn. That's interesting. That is really interesting. No wonder you need to import the string library for this to work. Okay, yeah, that's very cool. I want to see if. Okay, when we discover strings, I think it's become more necessary, since we know that array is just string is an array of chars. So yeah, okay, that's great. Okay, so we're hitting the 1 hour 30-minute mark, so I'm going to probably pivot into something else now. Probably going to read this embedded C book now. Okay. Okay, so these are the same thing, right? So these are the same thing in C. So this is just different. So is there any difference between Actually, I'm not sure. White space for okay. Okay, good. Okay, so I'm gonna, yeah. All right. So I'm gonna take a quick 5-minute break here. Yeah, and then we're going to move on to this book for embedded systems. Yeah. We're gonna start from the beginning though. Okay, so I'm going to turn off my audio for a little bit. So yeah. All right, guys. So we're back. I'm back. Just quick 3-minute break, and then yeah. So let's continue on. Let me shut the door real quick. Okay. Okay. So let's begin. So this is Making Embedded Systems by Alicia White. I read a thread on Reddit about this. Supposedly, it's a pretty good book for embedded stuff. So right here. So yeah, let's get started. This is my first ever book on embedded. I don't know much about embedded systems at all. I took one course in computer organization in university, and I did enjoy the course. So I hope to go into this field a little bit more. Yeah, so let's begin. Okay. So, embedded systems are different things to different people. To someone who has been working on servers, an application developed for a phone is an embedded system. To someone who has written code for tiny 8-bit microprocessors, anything with an operating system doesn't seem very embedded. I tend to tell non-technical people that embedded systems are things like microwaves and automobiles and software, but aren't computers. Most people recognize a computer as a general purpose device, perhaps easy. An embedded system is a computerized system that is purpose-built for its application. Damn. Okay. And I'm probably going to work on a project soon after I get a little bit of the basics done. So I think first month will just be a little bit more theory stuff. And then next we'll move on to practice. Okay. So we can think of an embedded system as sort of like just a more specific computerized system. So instead of a computer has has its own memory, has its own like processor and whatnot. It's hardware for it's very specific hardware. Embedded system is more like it runs software. It's hardware that runs software, but it's not necessarily a computer itself. For instance, let's consider CPU that runs more. At the same time or in real time. All right, so an embedded system is basically a computerized system, so it has both hardware and software, but it's built for a narrow application. And for this reason, like certain the hardware and the software has constraints in this manner. So hardware and software. So, like for example, less specific CPUs, memory efficient, Okay, perfect. Right. So, okay, so that's what high level overview what an embedded system is. Okay, so embedded systems are special, offering unique challenges to developers. Most embedded systems are developers develop a toolkit for dealing with constraints. Let's look at the difficulty associated with developing an embedded system. Once you become familiar with how your embedded system is limited, we'll start with the principles. Okay. Use cross compilers. Use cross compilers. All right. So embedded systems use cross compilers. Although cross compilers are on your desktop, okay. Cross compilers, the compiler will so it's like okay. So let me go back. So okay. So embedded systems use cross compilers, right? Compile, produce machine code. Yeah, because at the end of the day, we are using hardware from external hardware in an embedded system. So yeah, okay. If you were to debug software running on a computer, you could compile and debug on the program. The system would have enough resources to run the program. In fact, the hardware wouldn't know you were debugging. In addition to cross compile, you'll need a cross debugger. Okay, so we have to use a cross debugger. Also, so you also need cross debugger. So this is which communicates special processor interface. Yeah. So JTAG. Okay, so basically, the cross debugger is a special like interface which communicates with the hardware interface of this embedded processor. Yeah. So that's basically how you can debug in a way the hardware on the embedded system. Processor must expand on the debug interface. Okay, so you have your source.c file. You cross compile and link it. Yeah. Okay. You image file for processor. So you load that code to the processor and it goes in the code space. I think I'll probably go into this more in depth in the book, but yeah. Look through the code, look for variables process. Yeah, I'm not sure what these mean, but I guess we will figure out. But it is limited by. It is limited though. Yeah, it is kind of limited. The device that communicates between your PC and the embedded processor is generally called the hardware debugger performer and JTAG adapter. To avoid buying a debugger or dealing with processor limitations. printf. Oh yeah, or although some sort of lightweight logging into an otherwise unused communication port. Although incredibly useful system while leaving some. Sure enough, writing software for an embedded system can be tricky as you have to balance all the needs of the system against the hardware. Making software debuggable and somewhat hostile. Chapter 2. Okay, next is the resource constraints. So, an embedded system is designed to perform a specific task, cutting the resources it doesn't need. So you have to consider, yeah, okay, there are certain resource constraints with embedded systems. Okay. So memory, code space, processor cycles or speed, power consumption, processor peripherals. The added burden of cross-debugging can be frustrating. During board bring up, the uncertainty of whether a bug is in the hardware or software can make it difficult to solve. Unlike your computer and the software you may write. Once development and testing are finished, the system is manufactured, which is something most pure software engineers never need to consider. Supporting manufacturing is one way you can make sure the system created gets reproduced high fidelity. After manufacture, the units go into the field. With consumer products, that means they go into millions of homes where any bugs you create are enjoyed by many. With medical, aviation, or other critical products, your bugs may be catastrophic. You get paid to do so much treatment work. With scientific or monitoring equipment, the field could be a place where the unit cannot ever be retrieved. So it had better work. The life your system is going to lead after it leaves. Something was considered as the software. After you've figured out all these challenges and determined how to deal with them for your system, there's the largest challenge, one common of all branches of engineering: change. Not only the product's goal change, but the need of the project also changes throughout its lifespan. In the beginning, you may want to hack something to get it tried out. Right. Creating a system that is purpose-built for application has an unfortunate side effect. The system might not support as the applications morph. Engineering embedded systems is not just strict constraints, but also system. The goal of figuring out which of these constraints is likely to be a problem later in the product development, you'll need to predict. Right? Okay. Financial constraints as well, right? Harder to debug. And will vary over time. So embedded systems can seem like jigsaw puzzles that interlock. If a sensor X can talk about a communication channel Y, those are separate things and good candidates for being separate subsystems. Objects, we can do some testing on them. I've had good, excellent QA teams for some projects. Okay, so to confront, you good documentation. So modularity, so splitting it up, splitting into different subsystems. And test quality code. So think about testing. Okay. And there's just okay. But wait. Okay, so okay. But wait, you say. I already have a working system built with an Arduino or Raspberry Pi Pico. I just need to figure out how to ship it. I get it. The system does nearly everything you want it to do. The project seems almost done. Off-the-shelf development boards are amazing, especially the maker-friendly ones. There are many tasks I've forgotten at this stage. How will the firmware update? Does the system need to sleep? Do we need to watchdog? Custom board. It is removing the programming. I see. Okay. Okay. There are many excellent resources about design patterns. Okay, so that. Here's a computer with a compiler and editor, please. In many embedded systems projects, you have to develop a system from scratch. With the first part of the task, I look for a candidate who can take a blank slate and fill in the basic functions, even in I want to have them. So you better know the language on your resume. Any of them are fair game for this question. Which header file to include using command arguments and C. Find and fix syntax errors based on compiler errors. Where we can start moving into an embedded system. Hamilton answer, the program run. With an explanation of why these steps are important. An electrical engineer who asks this question may give his bonus points again. I'm not too sure about all this stuff. Okay. So. Okay. Right. Oh my god, I'm so. Yeah. Yeah, you can't do. Yeah, it's been a while. I should probably review this when I have the time. So, strings, so just an array of chars. Yeah, it's been a long time since I've been in this language, so it's like char. So isn't that char name? Incomplete. Okay. So yeah, okay, I gotta review strings and C. It's been a while since I've done this, so I'll come back to this question hopefully next time. I think that's probably the next lesson for the next episode. Probably just review strings real quick, because yeah, it's been I'll admit I'm a little bit sad that I don't know this, but it's okay because I'll just learn it. So let's just learn right now. Why not? C strings. You have a C string. Okay, so compiler to work. Okay, so oh shit. Oh man, what am I doing? Oh shit. This city io.h stdio.h. So we'll be like, okay. And that's strange. Oh. Okay, there you go. So you can't just write. I guess that's the fundamental misunderstanding of scanf. Let's see. Okay. So it's just form. You can't write like stuff. That's not how. If you, it'll probably pollute it, right? The format. You can only put the format specifier right here. So okay. So we got that. I better learn it now than in an interview. So. Get rid of this. Okay. So before the main function, so we have the only thing we have is realistically so we have to include the standard C libraries for input and output, and also for string because we might need that. But I don't think we even need, because this is more of like, that's more of a C++ thing. I just realized this. Yeah. So there you go. Right. An array string is just an array of chars with the null pointer at the end. Okay, so chapter 2. Okay, I'm going to quickly use the washroom. Be right back. All right, so we're back. Okay, so I'm going to start chapter 2 now, creating a system architecture. Okay, so even small, nice embedded systems have so many details that it can be difficult to recognize which patterns can be applied. Okay, so yeah, so depending on your experience level, the first few projects you design will be based on other projects, based on the existing platform with some changes. So like, yeah, so like think about like STM32 or like, I think is what they're talking about, right? And this is some microcontroller that's already existing in the market, right? In this chapter, we'll look at a different way of viewing the system in an effort to design better embedded software. We'll create a few diagrams to describe what our system looks like. Embedded systems depend heavily on their hardware. Unstable hardware leaves the software looking buggy and unreliable. This is a place to start, making sure that we can separate any changes in the hardware from bugs in software. It is possible, and usually preferable, to go the other way, looking at the system functions. Low-level hardware interfacing software to recite that your product depends on. Okay, yeah. Let's do this again. Okay. There are two ways to go about archetype. Okay, yeah, sorry, 1 second. Okay, and quick thing. So I want to go over what does your text for. So joint test action group. So it's like an interface. There are two ways to go about architecting systems. One is to start with a blank slate, with an idea or end goal but nothing in place. This is composition. Creating these system diagrams from scratch can be daunting. The blank page can seem vast. The other way to go is architecture taking. Okay. Okay, so there's four types of diagrams. This is more like a systems design thing. Oh, sorry. Okay, so context diagram, block diagram. And origami diagrams. And layering. So let's go over each one. The first drawing is an overview of how our system fits into the world at large. If it is a children toy, the diagram may be easy, a stick figure and some buttons on the toy. Okay, if it is a device providing information, network of seismic sensors with an additional output to local scientists, the system is more complicated, going beyond the piece you are working on. Local scientists, you have my device, goes onto server. Okay. A high level context of how the system will be used by the customer. So it's about relationship between user. So stuff like I/O, system. The design is straightforward at the start because you're considering the physical elements of the system. You can think of it in an object-oriented fashion. No matter whether you are using an object-oriented language to model your software around, each chip is attached to the processor as an object. Think of the wires. Start your design by drawing these boxes. by. This is episode of communications. The next step is to add a flash box inside the processor to indicate that we'll need some very specific. Okay, figure 2.2 shows us some of a schematic, beginnings of a software block diagram. Not the shop. This point is that we want to see how the high-level items determine objects will integrate. Keep the details in mind, particularly where the details may have system impacted, but try to keep the details out of the diagram if possible. The goal is to break the system down from a complete thing into bite-sized chunks you can summarize enough to fit in a box. The next step is to add some high-level functionality. What is each external chip used for? This is simple. We can put a box on it to represent the display assets. It doesn't have a notch. Elements. Damn, this is like, well, I'm not 100% sure how this is going to work, but we'll see. After you've sketched out this diagram on a piece of paper or on a whiteboard, probably multiple times, the box never end up being. Please still think about how all this is wrong. Looking at other types of drawings may show you some hidden ugly spots with critical bottlenecks, poorly understood requirements. Start your design by drawing these as boxes where the processor is in the center. The communication objects are in the processor and each external component is attached to the communication object. Okay, so I see. Very good stuff. This is very cool stuff. Okay, so communication objects are in the center. And each external component, okay, an external component outside. So okay, so again, just to recap, so context diagram is just a relationship between user. So think about I/O. So like you have a device of like for together like meteorological data or something. You're gonna be like the information from the actual meteor itself will be sent to like a local scientist. The server will be sent to the emergency service. Okay. This is kind of weird to think about this in the abstract, and I don't know why the author starts off with this stuff, but I'm just gonna trust the author. Like, I guess it's just the beginning. We're not meant to truly understand it for sure. Organogram. Okay, so an organogram. Sorry, that's what it's called. Okay. So you have the processor and all that. So I'm guessing, yeah. Okay, so you have your buffer, LCD drivers, stuff like that, and then you have the other peripheral devices, so like the backlight or like LCD, LEDs, all that type of stuff. Okay, starting to see how this is work. Okay. The next type of software architecture diagram, organogram, looks like an organizational chart. In fact, I want you to think about it as an org chart. Like a manager, the upper level components tell the lower level ones what to do. Communication is not only one direction. The lower level pieces will act in the order of the best of their ability to provide requested information, notify their boss when errors arise. Okay, this is control dependencies. So the main, okay. So like a hierarchy. Organogram. Okay, so you have the main, for example, you have the main program and you have the display. So the main program will influence the display, and then which will influence the sensor and the logging. So the display will affect the rendering, and by rendering week that'll affect what text to display, what images. Okay. Visual flash. Okay. I'm sort of understanding this, but it's weird when you don't know what flash or like SPI actually mean. Good stuff. Okay, so we Okay. Let's say that your team has determined that the system we've designing needs to each to have a serial number. It is programmed in manufacturing and communicated upon request. We could add another memory chip as a component, but that would increase cost, board complexity, and software complexity. Hmm. Okay. Okay. Yeah, so like it's basically like a hierarchy, I guess. If the logging system needs to get a serial number. Yeah, okay, I see. You're essentially. I might need to review this a little bit later. I think I sort of understand it. In the last architecture, drawing blocks looks for layers from present objects by their estimated size. They send another diagram start with a paper and pencil. Start at the bottom. Okay. So this is like a size diagram. Okay. Okay, let me read this one more time. Okay. Start at the bottom of the page and draw a box for things that go off the processor, so their communication boxes to spy and stuff. If you anticipate that one is going to be more complicated, then we'll make it larger. If you aren't sure, then make them all the same size. Next, add a diagram items that use the lowest layer. To control the bits that use below it becomes larger. Okay. Okay. Oh shoot! What the heck? Okay. I initially had the rendering box much smaller because moving data from the flash Easy. However, once rendering box I control all bits and pieces below it, it becomes larger. And sure enough, on the project, oh, okay. Yeah, okay. So like essentially you just take the information from your organizational diagram and then you just put them onto what's called layering diagram and decides essentially the complexity, I think. So in theory, the rendering should be the most biggest thing, right? Yeah, which it is, right? Right. Okay. Organize them by size. Oh my god. Okay, I see. Took me a while to realize this. All right. Okay, so and if they're used together, then you put them together. So if you have rendering, for example, it's text, file, images, generated graphics, uh, fonts, image. Yeah, they're gonna be all related to each other, right? LCD, yeah. Parallel. Okay, I'm starting to somewhat. I'm starting to somewhat understand what's happening here, but yeah, we're probably gonna need a little bit more. I probably need to do more. I'm going to read the section again because it's kind of difficult to understand, and especially because we don't know all the components yet. So, yeah. The diagramming process leads to interfaces that don't depend specifically on the content or behavior of the modules they connect. We use different architecture drawings to figure out the best ways for these interfaces. Each box. Man. Oh, shit, sorry. Okay. Okay, so now we're talking about designing for change. Okay. Test action group. In the example system, the LCD is attached to the parallel interface. The LCD is attached. Okay, so in the example system, okay. There's only my one other op. The LCD attached to the parallel I/O. Oh, liquid crystal display. Okay, so it's this thing. All right. Okay, so that should parallel the parallel interface. All right, so okay. Conversely, okay, so you can just like get rid of it, I guess. So you can not get rid of it. You can like just hide it under, so you can be like, you can have like an interactive diagram, and you can just be like, okay, so when you press LCD, it opens parallel interface. Perfect. That's okay. We have 13. Okay. Looking for things that can be split off and accomplished by another person will help you identify sections of the code. In the previous section, use a top-down view of the model to restrain another person. Okay, so you have to think about okay. The minimization. Okay, so it's like we want to have like less complexity. Essentially, you will just want to minimize the complexity of each section. So if you have one guy working on the, let's see, you have one guy working on the parallel, just the, I don't know how I think about this. So like, if you have one person just working on the sensor, one person is working on display. Like we know how the sensor will interact with main, right? So if one person works on sensor, then that will lead to easier work, right? Because they know, okay, sensor will just influence main. So less work, less complexity when it comes to thinking about other systems if you were to divide the tasks. All right, good stuff. Good stuff. Okay, so we can go bottom up too, right? But driver, I'm not too familiar with drivers. Interface to. Yeah, I'm not. I'm not too familiar with this stuff. What the heck? I'm not sure why this book. Okay. Okay, I see. I see what's happening here. So your definition depends on specificity. It is pretty specific in most modules. The drivers. Let me reread this one second. And let's try. Independence sometimes the best you can. This is interesting. This is very interesting. Okay. Okay. It's quite a bit of information here, and I'm getting kind of tired. So. everybody. So I guess since we're nearing the 2 hour 30-minute mark, I guess I will end it soon. So yeah, so today to summarize what we did today, I guess. So we did quickly review through a bunch of array stuff in C, which is good. Learned a decent amount of arrays, especially direct explicit initialization, and also the pointer decay, and also stuff like oh yes, yeah, especially pointer decay and size of. That's very key stuff. It's probably didn't know memset as well. I'll probably compile all my stuff I learned in a document. Also basics of embedded systems, which is good. I'll probably review this on my own a little bit, and then hopefully next time I'll have better resources. I kind of did some of this on the fly, so I hope it wasn't too confusing. But realistically, nobody's gonna watch this anyway. So yeah, thank you. If anybody made it to the end, thank you for listening. This is more of like a pilot episode. Usually I'll probably live stream these later on, but yeah, I hope you enjoyed this. Yeah, best of luck. And I'll come up with the next episode hopefully tomorrow. Yeah, thank you. So I'm gonna stop recording in 3, 2, 1.